This is part 2 of the redox topic from AQA Year 12 Chemistry. In the first part, we looked at the general introduction, some of the key words, and we also identified how we can work out the oxidation states of a range of compounds based on a set of rules. If you're happy with everything that's in there, it's now possible to move on and look at the next step, and we're going to start by looking at building half equations. Now, half equations are an important means of recognising whether something has been oxidised or reduced. But before we get on to that, we're going to have a little bit of practice and review of what has come before. So I'd like to take a look at this equation. Can you please assume that everything ionic is aqueous in this reaction, please? When you're ready, move on and see how you've done. Now, the reason that was an important distinction is that for an ionic compound to break down in an ionic equation, it needs to be molten or aqueous. If it's solid, it would not break down at all. But you can see here that I've broken down my FeCl3. I know the Fe is plus 3 because my 3 Cl's are 1 minus each. I know that my K is plus 1, so I must be minus 1 in this case. I know that the Fe must be plus 2 on the right hand side because it's with 2 Cl minuses. And I know I'm not going to break down my I2 because that's covalent. Now straight away I can now also get rid of spectators, things that have no part to play in the overall reaction. And if you look, you've got 3 Cl minuses on the left hand side. You've also got 3 Cl minuses on the right hand side. If they're not changing, we're not going to include them. But they're not the only spectators. We also have K+. Now that leaves us with the overall ionic equation that we see here. Fe plus 3 plus I minus goes to Fe plus 2 plus half I2. And it's now possible to break those down into their half equations. So my first half equation is going to be the Fe3 plus going to Fe2 plus. My second half equation is related to the iodide going to the iodine. But they're not balanced. I need to balance the half equations with charge. So I do that and I add my electrons. And we can use this now to recognise what has been oxidised and what has been reduced. The ion 3 has been reduced to ion 2. We know that for two different reasons. One, it's gained electrons, and two, we have reduced its oxidation state. Both of those tell us its reduction. In the I minus, it's lost electrons. We know that because the electrons are on the right hand side of the equation. But we also see that we've increased the oxidation state. For both of those reasons, it's oxidation. Moving on to the second example, have a go at doing the same thing. Again, assume that anything ionic is aqueous. So we have got here our Fe2O3 breaking down into Fe plus 3 and O2 minus, my Al2O3 breaking down into Al plus 3 and 3O2 minus. Once again, I have spectators. And I can get rid of the 3O2 minus. That allows me to go to the overall equation, ionic equation. And from there, I can break this down to the two half equations. Now they're not completed. Once again, I need to balance with electrons to balance the charge. So I add those in. And you can see actually that these numbers could have been broken down. They could be halved. I've simply followed through the balancing of the equation. But we can see here that the Fe plus 3 has gained electrons, which is reduction because oil rig tells us oxidation is loss and reduction is gain. And the aluminium has been oxidized to Al plus 3. Once again, we can look at the change in oxidation state to show that that's the case as well. But we're going to move on now and we're going to look at how we can build half equations. And the great news is there are 4 simple rules that you will follow. And I would recommend that you consider all 4 of these rules every single time and get into that systematic route through. We're going to take a look at a worked example, and we've got here Fe going to Fe plus 2. Now, rule 1 is to balance the species with a variable oxidation state. In this case, that's iron. It's already balanced. Rule 2 is to balance oxygens by adding water. not required. Rule 3 is to balance hydrogens by adding H+, not required. So I get to rule 4, which is to balance charge by adding electrons, and you can see that I've added 2 electrons to the right-hand side. If we take a look at another worked example, we have got here sulfuric acid going to sulfur. Now, once again, rule 1, the variable oxidation state species is S. It's already balanced. This time I do need to balance the oxygens. I've got 4 on the left, so I need 4 H2O on the right. Rule 3, I do need to consider because I need to balance hydrogens. I, at the moment, have got 8 on the right and 2 on the left. So I need to add 6 H pluses. I will always balance the H's by adding H plus. And finally, rule 4, I balance the charge. And I do that by adding 6 electrons on the left-hand side. So there are a number of these examples that we are going to work through. Let's take a look at this one. Copper 2 going to copper. So to review it, I'm now going to bring the rules back. Remember, you will need to learn these rules. And I'm going to start by building my equation up with what we've already been given. Cu plus 2 goes to Cu. Rule 1, balance the species with a variable oxidation state, copper. That's done, we don't need to balance it. Balance any oxygen. There is no oxygen. That rule is done. Balance the hydrogens. We don't need to do it. So we're left with balancing charge. And I've got plus 2 on the left and 0 on the right, so I'm adding 2 electrons on the left-hand side. Next example, pause and give it a go. Okay, going to bring the rules up once again, and we have got here Al going to Al plus 3. Rule 1, balance the species with a variable oxidation state. That's Al, that's already done. Rule 2, balance the oxygens by adding water. There are no oxygens. Rule 3, balance the hydrogens by adding H+. There are no hydrogens. So finally, I balance the charge by adding electrons. And I'm adding 3 electrons on the right-hand side. My half equation is done. Next example, pause and have a go. Okay, going to bring the rules up once again, and I've put the equation in. My MnO4 minus going to Mn plus 2. So the species with the variable oxidation state here is Mn. There's 1 on each side. That rule is completed. I'm going to balance the oxygens by adding water. I've got 4 on the left, so I need 4 H2O on the right. I'm then balancing the hydrogens by adding H+. I've got 8 hydrogens on the right, so I need 8 H+ on the left. And finally, I'm balancing charge. My total charge on the left is plus 7. On the right, it's plus 2. So I need to add 5 electrons to complete the balancing. Next example. And again, let's take a look at the answer. So, I've got the rules there once again. H2SO4 to SO2. Rule 1, balancing the sulfur, done. Rule 2, balancing the oxygens. I need 2 H2O on the right-hand side to take it up to 4. Rule 3, balancing the hydrogens. So I now need to add 2 H+ on the left. And finally, rule 4, I balance the charge by adding electrons. I've got 2 E- on the left-hand side. Next example. And again, let's take a look at the answers. Rules are provided so we can work our way through. And in the first instance, my sulfur has already been balanced. Rule 1 is done. I need to balance the 4 oxygens, so I add 4 H2O. I need to balance the hydrogens. I need 6 more hydrogens on the left-hand side. And I need to balance the charge, so I need 6 electrons on the left-hand side. Next example, sulfuric acid again. And once again, I have got the rules up, and we're going to go through. The sulfur is already balanced, tick. We have got 4 oxygens on the left, we need 4 H2O on the right. We've now got 10 hydrogens on the right, so we need 8 H+ added on the left. And to balance the charge, we now need 8 electrons on the left. Next example, Dichromate 6 ions going to Cr+3. So let's add the rules in, and there is the start of the equation. Rule 1, we've not had to use this much at all, but I've got 2 chromiums on the left, so I need 2 Cr+3. I'm then going to balance the oxygens by adding 7 water on the right. That means I'm going to need to add 14 H pluses on the left, and that then means that to balance the electrons, I'm going to add 6 electrons on the left-hand side. So then we move on to another example. And once again, I'm going to bring up the rules. So in this case, once again, rule 1 does apply because I've got 1 chlorine on the left and 2 on the right, so I need 2 HOCl. Now that means I need to balance the 2 oxygens on the left with 2 H2O, and when I look at my balancing of hydrogens, I've got 2 and I've got 4, so I need 2 more on the left. And then finally, I'm going to balance charge by adding 2 electrons on the left. And that takes us to the end of how we balance half equations. Some more complicated, some more straightforward there. Every single one of those, there is the capacity for it to come up in the exam. Going to move on now. I'm going to look in the final section of this video at how we can combine those half equations. And you'll be pleased to know that once again there are a set of rules. So we've got the rules here that you're going to follow through, have a read of them, maybe jot them down. I'm going to show you a worked example, and then you can have a go at some. So the worked example. I have got here iron being oxidized to iron 2, and I've got manganate 7 being reduced to Mn+2. First of all, I'm confirming that one of them shows oxidation and one of them shows reduction, because that's absolutely vital for the 2 half equations to be combined. Step 2, I need to make sure there's the same number of electrons in each one, because they've got to cancel out. They've got to be spectators. So to do that, I found the lowest common denominator of 2 and 5, and that takes me to 10 electrons. So I multiply them up accordingly. Now, once I've combined them, I can then set about removing the spectators. And the only spectators here are actually the 10E-, and that takes me to my final overall ionic equation, built from the 2 half equations provided. So in the following examples, what I want you to do is have a go at building the half equations, then combining them, then identify what's oxidized and reduced. But I also want you to say what's acting as an oxidizing agent and what's acting as a reducing agent. And the information in blue here is really important. But I'll talk a little bit more about oxidizing and reducing agents as we continue. So, first example for you to have a go at. And I'm going to bring the rules up once again. So I'm going to build the 2 half equations, and that is going to be Fe to Fe2+. Well, I need the 2E- to balance it. On the Cu2+ to Cu, I need 2 electrons on the left to balance it. Now, what I can next see is that I've got 2 electrons in each of them, so I don't need to do any multiplying up. I can simply combine them as they are. Now I can see that the Fe has become Fe+2. That's an increase in oxidation state, so it's oxidized, and my copper 2 has been reduced to copper because I've reduced the oxidation state. But I can also tell what's been oxidized and reduced from the half equations, depending on whether electrons have been lost or gained. So you can see that there. And finally, what's an oxidizing agent and what is a reducing agent? Well, whatever is oxidized is the reducing agent. Whatever's reduced is the oxidizing agent. And remember, oxidation is loss. So when we talk about a reducing agent, the reducing agent is losing electrons, but we change the context and we say that it's donating electrons. And an oxidizing agent is itself reduced, but when we talk about an oxidizing agent, rather than say gain electrons, we say it will accept electrons. And the idea of donation and acceptance gives us the idea that they are acting on something else. Okay, next example. And once again, we're going to have a look at the answers now you've had a chance to try it. So I start with my two half equations. Now, you've already done this one earlier in the activities, but I need to balance the chromiums, then I balance the oxygens, then I balance the hydrogens, and then I balance the electrons. In the ion 2 to ion 3, I'm going to balance that rule 1, rule 2, rule 3, not required, so I balance the charge with electrons. Now in this case, I've got 6 electrons in the top half equation and only 1 in the bottom one. So I need to multiply the bottom one by 6, and I multiply everything in there by 6. At that point, I combine everything from the left-hand side of both equations, everything from the right-hand side of both equations, and we end up with this. Again, you'll note the 6Fe plus 2 and the 6Fe plus 3. There are no other spectators. I've got rid of the electrons, so we can look at what's being oxidised and what's being reduced. Well, the chromium was plus 6 and it's gone to plus 3, so it's been reduced. We also know dichromate 6 is reduced to chromium 3 because it's done via electron gain. And the ion 2 has been oxidised to ion 3, it's lost electrons, and we've increased the oxidation state. And similar to the earlier examples, the oxidised species is the reducing agent, and the reduced species is the oxidising agent. Next example. And now let's add the rules, and let's begin building our half equations. Again, you've already done this example earlier in this video, so I don't need to balance the manganese. I do need to balance the oxygens. I do need to balance the hydrogens, and I do need to balance the electrons. In the Fe plus 2 to Fe plus 3, rules 1, 2 and 3 for building half equations are already done. No action is needed, so I balance the charge with electrons. In this case, I can see I've got 5 electrons in the top one and 1 in the bottom one. So I need to multiply the whole of the bottom equation by 5. That will allow me to have the same number of electrons on each side, so they cancel out. At that point, I can build my overall ionic equation. And once again, my Mn has gone from plus 7 to plus 2. So that's the reduced species. My Fe plus 2 has been oxidised to Fe plus 3. The oxidation state has gone up. But I can also see from the half equations what's being oxidised and reduced based on electron loss or gain. And finally, the species that's reduced is the oxidising agent, and the species that's oxidised is the reducing agent. Next example. And we'll go to the steps you're going to go through. My copper to copper 2, rules 1, 2 and 3 of building half equations not required, but I'm going to balance the charge with electrons. My HNO3 to NO2, my N's are already balanced. I add water to balance the O's. I add H plus to balance the H's. I add electrons to balance the charge. At this point, I can see that I've got 2 electrons in the top half equation and 1 in the bottom. So I'm going to multiply the bottom one by 2. And when I combine them, I end up with this. Electrons are gone. Now, my copper has been oxidised, which means it's acting as the reducing agent. My nitric acid, HNO3, has been reduced to NO2. The N has gone from plus 5 to plus 4. It's been reduced, so it's the oxidising agent. And we're going to finish off by looking at something called disproportionation. And for this, I would like to take a look and identify what has been oxidised and what has been reduced. So I'm going to go through and put all of the oxidation states in. My hydrogen remains plus 1 on both sides. It's not in a metal hydride, it's not on its own, so it will always be plus 1 in those circumstances. My oxygen has changed because my oxygen is minus 1 in hydrogen peroxide. That's one of the exceptions to the rule. but it's -2 in water, so that means that the oxygen has been reduced. The H2O2 has been reduced to H2O. The oxidation state has been reduced. But in oxygen, the oxidation state is 0 because it's an uncombined element. So my H2O2 has been oxidized to O2. The oxidation state has increased. So I can see the reduction here, but I can also see oxidation here. Let's take a look at another example of disproportionation. In this case, my H's are +1 all the way through. My oxygens are -2 all the way through. My chlorines, well, it's 0 on the left. In HCl, it's -1. And in HOCl, it's +1. The chlorine has been both oxidized and reduced. That's what disproportionation is, when a species is both oxidized and reduced in the same reaction. So that takes us to the end of the redox topic. Well worth going back over and reviewing regularly. Hope you find that useful. Thank you very much, and goodbye.